Hello, welcome to my channel. So in this video, we'll try to answer few questions or few interview questions. These are most favorite question asked by interviewers. So in um, let us test our understanding. Let us test our understanding of RF from these questions. So first question is, what is RF or what is radio frequency? We all know that it's in the electromagnetic frequency. We have frequency range from few megahertz to up to gigahertz range. So that is the frequency, radio frequency. In radio frequency, we are interested for wireless communication, like from few megahertz to uh, hundreds of gigahertz. So in radio frequency, in radio frequency, we have yeah we have something like this: electric field and magnetic field. Those are perpendicular to one another, and the wave is traveling in the direction that is perpendicular to both of them. Now again, we all know that. So suppose this is a sine wave. From here to here, this is one complete one complete cycle, and this is called wavelength. All right, this is the wavelength, and the frequency and wavelength, these are dependent. Okay, because we have something called, we all know that speed of light is equals to no, distance over time. So we can also write this as speed of light is wavelength, and 1 over time is the frequency. So we have this relationship here, that is speed of light is wavelength times the frequency. So what is RF? So what is the RF? RF refers to the range of electromagnetic frequencies from this to this. These frequencies are used for wireless communication because they can through free space over long distance. And one more important thing is, this radio frequency, they do not require any medium. They can travel in the vacuum or the free space. And here it says RF signals are in applications. Yeah, they can be used in such a in radio broadcasting, mobile communication, radars, Wi-Fi and Bluetooth, and of course in Wi-Fi and Bluetooth, we use frequency 2.45 gigahertz. So you can imagine uh, the frequency and its corresponding wavelength. We can, if this is frequency is given, then we can calculate the wavelength, because we have just seen speed of light is equals to wavelength times the frequency. If frequency is given, and we all know that the speed of light in space is 3 times 10 power 6 meter per sec, so we can plug this value here and calculate. Yeah, so let's go to the next question. Yeah, so it is, yeah, so in the question 2 is, what is the relationship between frequency and wavelength? So we just see frequency, I mean uh, you see this is a sine wave, and this is another sine wave. Okay, now from here to here, this is the wavelength, and from here to, let me, yeah, now we have another frequency here, I mean signal here from here to here, I have this wavelength, let's call this lambda, yep, lambda 2 and lambda 1. Now we all know that we have c, speed of light is wavelength into the frequency. That also means frequency is inversely proportional to the frequency. If frequency is higher, we'll have lower wavelength. Yeah, so this is the relationship between them. I mean, if their two corresponding crest or throw is much closer to one another, that means we have higher frequency. In that case, their wavelength will be shorter. So this equation confirms this. All right, so let's see the answer here. You see, frequency and wavelength are inversely proportional. Yeah, we have just seen that. And related by the equation, this, it says lambda is equals to c divided by frequency. All right, that means speed of light is equals to frequency into lambda. Yeah, we all know that, and c is speed of light, which is this times this. This relationship is extremely important in RF design because antenna size, transmission length, and PCB layout dimensions are often expressed as a fraction of wavelength. Okay, so you see, for example, transmission line length. So in PCB designing, there is something called critical length. For example, C divided by 10. I mean lambda, not C, but wavelength divided by 10. That means this is called critical length. For example, we are designing an antenna. Okay, suppose we have one transceiver IC, and we have to connect one antenna here. And please imagine, this is, we are designing this system in a PCB. So what we need, suppose this is IC, and from IC we need to connect the antenna. So there is a transmission line. Now what happens is that, so imagine we are working with 2.45 gigahertz. 2.45 gigahertz. For this we have corresponding wavelength of how much, and calculate wavelength of 2.45 gigahertz. Okay, we can calculate everything using pen and paper, but why should not use, okay, my bad. So it is around 12 centimeter. Okay, 12 centimeter. Now, yeah, 12 centimeter. Now what, uh, we got lem we got lambda is equals to 12 centimeter. Is it? Yep. Now 12 centimeter divided by 10, we have 1.2 centimeter. Please not 1.2 centimeter, which is around 12 millimeter. Now, if my length of this transmission line or the trace in the PCB is greater than this 12, uh, 12 millimeter, then it should be considered as a transmission line. What does it mean? It means it should have the impedance. For example, usually the impedance from this IC should be 50 ohm. If it is 50 ohm and my antenna is also 50 ohm, then my transmission length should also be 50 ohm. So that is why this wavelength, the calculation of wavelength is critical. And if anything, if we do not want to worry about this length of, I mean how, I mean this transmission line, and the characteristic or the impedance of this trace, or this copper trace, then it is better to keep its length lower than this lambda by 10. And again, there is another thing here. It says antenna size. Now we all know that, and some space here. You see, we need We all know, okay, I will be explaining monopole antenna in different slides. Basically, a monopole antenna, its length of the conductor is lambda by 4. That means if I want to design an antenna for 2.45 gigahertz like my Wi-Fi or Bluetooth application, we have just seen its wavelength is 12 centimeter. Okay, then the size of antenna should be lambda by 4 for monopole antenna. So how much it? So 12 by 4, which is 3 centimeter. So my length of conductor, it should be 3 centimeter or 30 millimeter, and it should have one ground plane, infinitely long ground plane. This is the theory, but we cannot have infinite long ground plane. For that reason, there is a technique called ground sleeve, which is uh, placed around this conductor, which acts as a ground plane, and it also has better directivity, better gain. We'll be see what is antenna gain and all in upcoming slides. So yeah, that's it. Let's see our next question. Okay, so what's an electromagnetic wave? We all know that what is electromagnetic wave. An electric field in this plane, um like this, and we have magnetic field in this. So if we have electric field in, suppose, xy plane, yeah, suppose we have our electric field in this direction and our magnetic field in a direction which is perpendicular to the magnetic field, then our propagation wave will propagate in a direction that is perpendicular to both of these. This is called an electromagnetic wave. It has electric and magnetic field both. It says an electromagnetic wave is a wave composed of time varying electric and magnetic field that are perpendicular to one another and also perpendicular to the direction of propagation. These waves do not require a physical medium to travel. Yeah, as we have discussed in our previous slides, they can travel in free space and can propagate through vacuum. In RF systems, electromagnetic waves carry information through modulation of amplitude, frequencies, or phase. Yeah, this is important. You see, we can definitely transmit the electric, we can transmit, we can definitely transmit EM waves, but it should have some information. So there is concept called modulation. What we do here, suppose we have high frequency wave, which is called carrier wave, and what we do here, we impose um, uh, a signal of our choice here. Okay, so as a result, we get sometimes AM signal, FM signal, that is amplitude modulation, then frequency modulation. So those are concepts like AM transmitter or AM radio, FM radio. This work on such principles. So in I mean, in my next video, maybe I will make a video on this topic. Now, yeah, this is important. So, what is a transmission line and why it is required? Now, what is the transmission lines? So, there are, suppose this is a conductor, two plates, and separated by some space, and maybe they have some dielectric material. For example, we have two-sided copper plate, so that is also a transmission line. Then we have waveguides. So those are called transmission lines. Basically, we have one conductor and dielectric, and then conductor. So these are called like coplanar transmission lines. Suppose our PCB, two-sided PCB. So these are called transmission lines. And why it is required? Because you see, when we work with higher frequencies, then their wavelength, okay, wavelength this, it becomes, for example, we are working with suppose 2.45 gigahertz, then wavelength becomes 12 centimeter, and in such case, in such this thing, you see, a transmission line is a structure designed to carry high frequency signals from one point to another with minimal distortion and loss. It becomes necessary when the physical length of the conductor is comparable to the wavelength of signal. Yeah, because you see now our wavelength becomes 12 centimeter, and if I design a board that is maybe around, I mean more uh, than that, then in such cases there will be introduction of like inductance and all. uh, there will be something like critical length. So in that cases we need to consider its impedance, characteristic impedance and all. I mean every trace of my PCB should be considered as a transmission line. So in that case I have to consider its impedance, so that there should not be any reflection, there should not be any power loss and all. So in that case there's a need for such transmission lines. And let me also tell, yeah, so this is there are many different types of different types of transmission lines are available, are do exists. For example, these coplanar transmission lines, for example, two layer PCB, and then we have this coaxial cable. In coaxial cable, this is the inner conductor here, and this is filled with some dielectric material like Teflon, and then we have a metallic sleeve here. So this is again, for example, coaxial cable, and then we have waveguide. In waveguide, this is a, imagine this as a cylinder, metallic cylinder. Here, RF frequencies like much higher than maybe like 10 or I don't know, maybe 50 gigahertz. This travels inside this KBT. So this is called waveguide. So these are some examples of transmission lines. Then, yeah, what is characteristic impedance? So suppose imagine we have something like coaxial cable here. Please consider this is the conductor filled with dielectric material, and this one is the sleeve. Now the thing is, characteristic impedance, which is denoted by Z naught, it is the ratio of voltage. Okay, the voltage to the current flowing through it, provided that this is infinitely long coaxial cable, we have or suppose we attached one load here. Suppose we have attached a load here, maybe some load here. This is our load. Suppose L is our load, and we have connected in such a situation that there should not be any reflection going back. That is called characteristic impedance. Let's see. Yeah. So a characteristic impedance is the ratio of voltage to current of traveling wave along a transmission line along a transmission line uh, which is infinitely long, yes, infinitely long, or terminated in a match load. Why it is? Because we do not need any reflection. If it is unmatched, there should be some reflection, so that is why it is mentioned match load. It depends on the geometry of the transmission line and the dielectric material. Yeah, that's also true, because we have, so there is a we can there is something like z naught equals root over L by C or C by L something. So that means it is purely dependent on the geometry of the transmission line. So yeah, you see, maintaining a constant characteristic impedance is critical to prevent reflections. We'll study more about this in upcoming slides. Now, what is okay? Now, why 50 ohm is commonly used in the RF system? I think many of us have, maybe we have worked with instruments like VNA or something like that, where we put 50 ohm impedance uh, to the one of the ends of such instruments while calibration and all. Now, like why 50 ohm? So it has a long history of 50 ohm. Okay, um, a long history, but there is another reason for choosing 50 ohms, like uh, for lower loss and like that. So let's see why 50 ohm is used. You see, the 50 ohm is standard. 50 ohm standard is a practical compromise between power handling capability and signal attenuation. Lower impedance, you see, lower impedance can handle higher power, but suffer higher losses, while higher impedance have lower losses but lower power handling. Though through historical development and standardization, 50 ohm becomes the most widely accepted impedance for RF equipment, ensuring compatibility between transmitter receiver antenna and test instruments. So okay, now what is VSWR and why it's so important? So voltage standing wave ratio. Let's see what is it is what what the VSWR is. So it's a measure of impedance matching between a transmission line and its load. Okay, it is defined as the ratio of minimum to maximum voltage along the line. Minimum to maximum. Okay, indicates perfect. Well, yeah. So there is some. Suppose mm, suppose we have a patch antenna here. Okay, we have something like this. This is feed line, and this is the radiating surface. Below I have one ground plane. Now the thing is, everywhere the impedance is different. You see, I this is the feed line. So the impedance here will be different to the impedance of this. You see, in such surface, there is uh, no path for the signal for the current to flow. As a result, current will be lower in this surface, but voltage will be higher. As a result, my impedance will be different, because impedance. So impedance is voltage divided by current. Now we have we learned that in such uh, in such area, in such region, I will have higher voltage and lower current. Why lower current? Because there is no path available for the current to flow. So that means I have higher impedance here, again here also, because it is a edge and no current can flow. So as a result, everywhere I will have different waves, which is also called the voltage standing wave. And this VSWR, you can see here, where I was, here, slide 14. Yeah, A VSWR of 1:1 indicates perfect matching. So, so it is a ratio of voltage of maximum voltage to minimum voltage along a line. Okay, I have lost every drawing that was present here. So yeah, that is what VSWR is. So let's go to our next question. So what is antenna gain? Yeah, this is very important. There is a concept of omnidirectional antenna, isotropic antenna, isotropic antenna. So what is isotropic antenna? Suppose imagine we have a small antenna here. Imagine it as a charge or something that can radiate in all direction equally. Okay, so this is actually not a real antenna. This is a hypothetical antenna, and it's it can radiate in every direction. Imagine it's a sphere. Okay, it's a sphere like this, and it can uh, emit the radiation in all direction equally. So this is called isotropic antenna. Isotropic antenna. But in real case, for example, consider we have something like uh, monopole antenna. It will radiate in some in this fashion. Uh, Suppose this is our antenna, which is in red color, and we have radiation pattern in this direction. Okay, in this direction. And again, please uh, view this um, as a 3D model. So it is actually it is a donut shape like radiation pattern. Now the thing is, in antenna gain, we call it antenna gain is efficiency times the directivity. That means this is the definition of antenna gain. That means with respect to this isotropic antenna, that is why many times we can see the antenna gain is uh, as represented maybe as like something like 10 dBi. This I this I sorry, this I is related to this isotropic antenna. That means with respect to this isotropic antenna, it has 10 dB directivity. So it says a antenna gain is a measure of how well an antenna directs or concentrates concentrates radio frequency energy in a particular direction compared to an isotropic radiator. It includes both the directivity of the antenna and its efficiency. Antenna gain doesn't imply amplification of power. Instead, it represents the redistribution of radiated energy. So that is what we have just discussed. Now, question 9. Why is RF not ideal for higher frequency RF designs? So what is RF? What is FR4? You might ask. This is called um, uh, I forgot the full form of this FR4, but basically, um, suppose we have two-layer PCB again, and the dielectric, okay, and the dielectric that is present. This is called FR4, but not exactly every two-layer PCB is made up of FR4. There are different types of material, dielectric material are also present. For example, Rogers, D, Droids, DT Droids or something. So the problem with FR4 is, suppose it is very much um, lossy, and if I vary from 1 to 3 gigahertz, okay, then its dielectric is not, not accurate. Not static. It keeps changing with the frequency as we go. Suppose maybe 5 gigahertz, then its frequency, its dielectric will vary with the frequency. That is why it is not recommended to use FR4 uh, in for high frequency applications. For that, I mean, way expensive material are also available, like Rogers. So that is recommended. And why we use FR4? because it's very cheap. I have also purchased few, say, a single layer and two layers piece. This is a copper clay made of FR4, and it is very cheap, around 20 to 30 rupees for like 15 by 15 by 10 inch. No, no, I mean 50 centimeter by 10 centimeter FR4 copper plate. Like one can purchase from 220 30 rupees. So that is why this is used it for this is used for lower for I mean low speed signal applications. Yeah, you see, FR4 is a low cost PCB material but has several limitations at higher frequencies. Its dielectric constant is not tightly controlled. Yeah, we have discussed this thing, and it keeps changing with frequencies and also temperature and manufacturer. Yeah, okay. It also has a relatively high loss tangent, um, which leads to significant signal attenuation at microwave frequency. For higher performance RF design, you see materials such as Rogers laminates are preferred. Yeah, we have discussed that thing also. So yeah, that's it. So thanks for watching, and I will upload another video in RF very soon. Thanks.